Okay, we're on nuclear chemistry. And last time we started talking about kinetics of radioactive decay. And as we talked about last time, pretty much all radioactive decay will follow first order kinetics, which basically gives you two typical equation to sort of follow. We have usually the natural log of A is equal to natural log of A naught minus KT. This is like your kind of final concentration. This is your initial. This is what is referred to in sort of nuclear chemistry as the decay constant. In regular kinetics, it's the rate constant. And T here is time. And with that, we do have a half-life equation that goes with first order kinetics, which is the half-life is equal to the natural log of 2 divided by the decay constant. And again, that is 0.693. You'll sometimes see it written as. As we talked about last time, very commonly you will oftentimes need to use sort of both of these formulas together. And very commonly you'll be given kind of the half-life, and you would use the half-life equation here to get the decay constant, which then you could put into this equation and solve for whatever you're looking for, initial concentration, final concentration, maybe even time. The thing that we talked about as well that's really important, especially with this, is in terms of time, is these two together here. They both have a unit of time in them. Typically, the decay constant has units of 1/seconds or 1 over some unit of time. And obviously, T is time. So you do want to always make sure that they are in the same units. Very commonly, especially in radioactive decay here, they are oftentimes in different units. Otherwise, again, you're going to be off. So you got to watch that kind of time value of it. Any questions on that there? I think we did an example there at the end. So let's take a look at another one here. Radon 222 is released into houses, assuming no loss or gain from leakage. If there's 10.24 grams of it in the house today, how many will be there in 5.4 weeks? The half-life here of radon 222 is 3.8 days. So take a moment there and see how much should remain after 5.4 weeks. All right, so let's take a look. So the good news is you don't have to really think about which equations to use because there's only two that goes with these. So again, we'll kind of look at our first order kinetics equations here. In this case, we do have our initial here, which is 10.24 grams. We do have our time, which is 5.4 weeks. And we are looking for what's going to be left over pretty much at the end. So if we take a look here, we're looking for this. We have that. We have that. We are missing the decay constant here to allow us to solve for it. That is where our half-life is going to come into play. So in this particular case here, if we go in, our half-life is 3.8 days equals the natural log of 2 divided by k. These two guys basically switch places, and that will get us that our decay constant here would be the natural log of 2 divided by 3.8. That's going to get us a 0.1824 reciprocal days, or the units. Once again, that's important because this unit of time is days and our time is in weeks. So we do have to do a conversion. And it really doesn't matter which way you want to convert to days to weeks or the weeks to days, whichever we want to go. I'm going to convert my weeks into days since I already have my decay constant in days. So 1 week, 7 days, I guess we'll go with. And that's going to get us here 5.4 times 7, about 37.8 days. And again, now both this guy and this guy are in the same units of time. So everything will cancel out correctly. Now we could actually just go in. So natural log of A equals the natural log of 10.24. As I mentioned before, in traditional kinetics, we do use molarity here, but really in radioactive decay here, use really any unit you want as long as they're, again, both the same. So it doesn't really have to be a concentration. In this case, we use grams. I think in the previous problem, we used milligrams. Minus our decay constant there are 0.1824 reciprocal days and our 37.8 days. All right, so kind of cleaning up the right-hand side there, we'll go natural log of 10.24 minus 0.1824 times 37.8. Going to get us the natural log of A is equal to negative 4.568. Going to E both sides there. That's going to get rid of that. Do a little bit of that action here. And that'll get us a sort of final concentration of 0.0104. These would be the same units as the initial, so these would be grams in this case. Any questions on that there? Obviously here it did get smaller, which is good. If we got larger, we're going definitely in the wrong direction here. Any questions on that there? Okay. So the next thing we're going to talk about here is we could actually use our kinetics here and do some radio dating. Let's figure out how old things are. We could do radiocarbon dating, and radiocarbon dating uses basically carbon-14, and basically it will decompose down into nitrogen, and it has a half-life of 5730 years or 5,730 years. Cost you do uranium 238 dating. Same idea. It has a half-life here of 4.51 times 10 to the 9 years. Sometimes based on how much lead is there to uranium, you can also kind of figure out how old something is. It works basically the same way as sort of the first order kinetics that we've been talking about previously. So for example, here, if we had an ancient skull that gives 4.5, and these units are units of radioactive decay here. So this is disintegrations per minute per gram of the C here is actually carbon. It is not degrees Celsius or anything like that. So it is per gram of carbon. And a living organism gives 15.3 disintegrations per minute per gram of carbon. If we want to know how old that skull is, once again, the per grams of carbon is important because that kind of tells us what half-life we want to kind of use here. So we would want to use the carbon-14 half-life in this case, which is 5730. And that's going to allow us to sort of solve what we need here. And it basically will work the same way. So initially here is our living. So a living organism there is going to be 15.3 disintegrations per minute per gram of carbon. Final, not so living there is going to be our guy at the end there, 4.5 disintegrations per minute per gram of carbon. And we want to know in this case T, basically how old is it? So from our first order kinetics equation, natural log of A equals the natural log of A naught minus KT. Once again, in this case, we actually have our initial and our final. We are looking for T. And once again, here we are kind of missing the decay constant to allow us to solve for it. But knowing that we're talking about grams of carbon in this case, we can again use our half-life there to figure out the decay constant. So once again, our half-life equation, natural log of T divided by the decay constant. Again, switching places these two guys gives us the decay constant, natural log of 2 over the half-life. And that's going to give us a natural log of 2 over, in this case, 5730 years. And again, we know to use that because we're talking about grams of carbon in this case. So natural log of 2 divided by 5730 will get us a decay constant of 1.21 times 10 to the, looks like 1, 2, 3, 4, -4. The units here are reciprocal years in this particular case. So 1/years are basically the units. Now that we have that, we again have pretty much everything that we need in this case. So we could plug it into our equation here. Natural log of our final there, 4.50 equals natural log of our initial 15.3 minus our decay constant 1 times 10 to the -4 reciprocal years and our t. When it's all said and done and we do solve for t, it will be in units of years in this case because of the decay constant. So we can go natural log of 4.5, probably punch that number in right would be good, 4.5. We're then going to subtract the natural log of 15.3. So basically, I'm just going to subtract that to the other side, and that's going to give me -1.223775 equals -1.21 times 10 to the -4 reciprocal years times our t. We're just going to divide that now to the other side, not forgetting to take the negative with it as well. And it looks like we end up with an ancient skull that is about 10,000 years old, give or take a couple of years there along the way. Any questions on that? So it's really still the same sort of kinetics equations that we used previously. The difference here is, you were kind of looking for time in this case. And a lot of times, as you can see here, you will be given something that's, again, not a traditional unit, but basically a unit of radioactive decay. Like we see here, disintegrations per minute per gram of carbon. They could also have one sometimes referred to as counts per minute per gram of something as well. So that's, again, another unit of radioactive decay. Any questions on that there? All right, so why don't you try one here? This is what we just did. All right. So we have they dated in civilization to 15,600 years ago. If a living sample gives 20 counts per minute per gram of carbon, what is the number of counts per minute per gram of carbon for a grain of rice that they found at this site? So once again, the key here is grams of carbon, basically the same half-life as we used in the previous one here. Again, that's another sort of unit of radioactive decay, counts per minute per gram of carbon. So why don't you give it? All right, so let's take a look. And again, in this case, because it's per gram of carbon, again, in their unit of radioactive decay, counts per minute per gram of carbon, we would use, obviously, the exact same one that we use here, which is our half-life there. And we would use it again for our carbon, and we actually can just borrow what we did here. We could actually use the same decay constant, which we're going to eventually need there, 5730. So our half-life here is going to be 5730 years. In this case, looking at our equation and what we are missing, we are actually looking for what the counts per minute will be at the end. So we're actually looking for this guy. We do have this guy. We do have this guy. And once again, we can use this in our half-life equation like we did on the previous problem to basically get our decay constant, which once again should give us the same exact number there, our 1.21 to our -4, I believe it was there. So our 1.21 times 10 to the -4 reciprocal years. So popping in our numbers here, our natural log of A, which is what we're looking for, equals our natural log of our living, which would be our initial. Not so living would be our final. And we'll use the same K that we determined last time because it will come out the same. And in this case, we do have our time here, which is 15,600 years. And once again, our units of time for both of those guys are the same, so we're good to go. Don't have to worry about any type of conversion. Again, cleaning up what we got going on there on the right-hand side, natural log of 20 minus 1.21 to the negative 4 times 15,600. Gonna get us a natural log of A is equal to 1.10813 if I punch that in right. And again, we're going to E both sides here. And that is going to get us our sort of final here of 3.03. Now, the units of this will be the same units as our initial. So these would be counts per minute per gram of carbon in this case. And again, this is our older piece of rice. It has been around a while, it has decayed a while, so it is not giving off as much radioactivity as our initial. What's your question? The half-life would be given a lot of times in these type of problems, yeah. Or maybe in a table or something, you might have to look it up, but yeah. Other questions? Or alternatively, you could technically be given the decay constant, but very commonly in these problems, half-life is more often given to you than just actual constant. Other questions? All right, questions on kinetics and radioactive decay. All right, so the next thing we're going to talk about is where does the energy from fission come from? Remember, a fission reaction is essentially a reaction where you have an unstable nucleus isotope there, and it's going to split off into typically two new nucleuses. It also will get you some neutrons that are released and also a lot of energy as well as usually released from that process. This process can be spontaneous, and something that's unstable will spontaneously go through this fission reaction. You could also cause it to happen by, for example, shooting something like a neutron at something that's stable, and then it doesn't get very happy when you do that, and it becomes unstable and will go through this sort of process. Now, during the process of nuclear fission, some of the mass of the nucleus is actually converted into energy via Einstein's equation here equals mc squared. M in this case was sometimes referred to as the mass defect, and we're going to talk about what that is in just a second. But essentially, it is the slight mass difference between the particles within the nucleus, the protons and neutrons, and the mass of the isotope. So there's a slight mass difference between those two. And basically, that gets kind of converted into energy. And C is the speed of light. I'll go with 3 times 10 to the 8 meters per second is good for me. Or you go 2.997 if you like that number. So, for example, a mole of uranium-238 that goes through fission will produce something like 1.7 times 10 to the 13 joules of energy. If you compare that to a typical or a very exothermic chemical reaction where we're just breaking and making bonds, it only produces about 10 times or 10 to the 6th joules of energy. So you do get a lot more energy sort of output, if you will, in a fission reaction. And again, it's because you're going into the nucleus and again, kind of converting protons to neutrons, neutrons to protons. So there's a lot more sort of energy display with that. Also why it's used in some reactions, again, in nuclear power plants and for other things as well. Now, that sort of difference in the mass of the sort of isotope and atom and the mass of really the particles that make it up is what is known as the mass defect. And like I said before, that's sort of what gets converted into energy through this process. The energy that is released from the nucleus when it forms is what's sometimes referred to as binding energy. A form of that is sometimes also referred to as nuclear binding energy. Nuclear binding energy per nucleon is also another measure of stability. So if you calculate the binding energy per nucleon, a reminder that nucleon is basically your protons and your neutrons, everything in the nucleus, also like your mass number essentially. That value, that binding energy per nucleon, is also another measure of stability. So the higher the binding energy per nucleon is, the more stable that sort of isotope is. Now, you could use Einstein's equation, as we will see here, to calculate the energy. There's also sort of a shortcut conversion version of it, and you maybe don't have to use Einstein's equation. And one is 1 mega electron volt is equal to 1.602 times 10 to the minus 13 joules. And 1 AMU mass defect is equal to 931.5 mega electron volts. So very common units of binding energy is one of two types of units. Joules per nucleon is a very common unit of binding energy, are mega electron volts per nucleon. So these are both sort of units of binding energy per nucleon. And like I said, these conversions are sort of based on Einstein's equation, and you just may not have to kind of use Einstein's equation, but you can do it either way. It will come out the same, and we'll take a look at that here in just a second. So for example, if we take a look at fluorine here, and if we look at the fluorine 19, and fluorine 19 has a atomic mass of 18.9984 AMU. So when we look at fluorine 19, a couple of things that we know. Fluorine's atomic number is 9, which means it has 9 protons. If we take the top number minus the bottom number, that's 19 minus 9, will tell us it has 10 neutrons. So these are the particles, again, that make up the nucleus. So if we take the mass of each of those particles in the nucleus, that difference between those particles and the mass of the actual isotope itself is what is known as the mass defect. So if I wanted to calculate the mass defect in this case, which by the way is sometimes just abbreviated with a little delta symbol in that formula for Einstein's equation, equals delta C squared. Sometimes see that. Well, we would take our 9 protons times the atomic mass of a proton, which is 1.007825. We will then add it to our 10 neutrons times the atomic mass of a neutron, 1.008665 AMU. And then we're going to subtract it from the atomic mass of this isotope, which is 18.9984 AMU. And again, this is going to give us our mass defect, which is, again, that kind of difference in the mass that gets kind of converted into energy through this process. So 9 times 1.007825 plus 10 times 1.008665 gets us something like 19.157. Kind of clean up that side there. And then if we subtract it from the mass of our isotope, we get a mass defect of 0.158675 AMU. And again, that is our mass defect in this case. So basically, you want to take the number of protons, number of neutrons within your isotope, times it by the mass of each of those particles, and subtract it from the mass of the isotope. That, once again, gives you your mass defect. At this point, we can figure out the energy, and we'll take a look at it maybe a couple of ways here. If I use E is equal to mc squared, the m in this case would be my mass defect, so I'm going to put that in 0.158675 AMU. I'm going to times it by the speed of light, 3 times 10 to the 8 meters per second squared. And if I multiply that there together, we end up with 1.428 times 10 to the 16. Now, if we look at the units that we end up with at this point, it is AMU, meter squared, second squared are the units. Now, a unit that is similar to joules is a joule is equal to 1 kilogram, meter squared, seconds squared. So we're actually very close to that unit, except that we have AMU. So we could actually get rid of the AMU here by using our friend Avogadro's number, 6.022 times 10, but not to the 23, to the 26 AMU. And that is because when we do it to the 23, that is like for grams, to the 26 is for kilograms. Yeah, so that's basically that conversion there. And that will cancel out the AMU, and that will get us here divided by 6.022 to the 26 to get it into kilograms. 2.37 times 10 to the minus 11 joules at this point. And that is the binding energy. Like I said before, very typically the binding energy is given joules per nucleon. So in this case, we would take this and divide it by the nucleon, which once again is a fancy way of probably saying just the mass number, which is 19. So 19 nucleons in this case. That's our protons and our neutrons. So we'll divide it by 19. Gets us a 1.25 times 10 to the minus 12 joules per nucleon. Stop any questions on that calculation there. Now, like I said before, that is a very common unit of binding energy. Also, mega electron volts per nucleon is also a very common one. So you could use, for example, the 1 mega electron volt is equal to 1.602 times 10 to the minus 13 joules. That conversion we saw on the previous slide. And if I divide it by that there, this will get us another version of it, which is about 7.79, we'll call it 1 mega electron volts per nucleon. So this is the nuclear binding energy per nucleon for fluorine 19 in both joules and mega electron volts. First off, any questions on that there? Now, as I mentioned before, if you do not want to kind of use Einstein's equation, you could actually use those conversions that we saw right here and just straight up kind of bypass using the equation. So if you wanted to do that, you would actually pick it up with the mass defect, and you would go the 0.158675 AMU. You then would use the conversion on that last page of 1 AMU of mass defect is 931.5 mega electron volts. That's just going to put you into mega electron volts right off the bat. 0.158675 times 931.5 gets you about 147.81 mega electron volts, which if you want at that point, you could also divide by the 19 nucleons. And again, with rounding, we're going to be a little bit different than what we had up there, but fairly close, 7.7, we'll call it 79 mega electron volts per nucleon. And again, that's pretty close, just a little bit difference in rounding. And at that point, you could then use your joules to mega electron volts conversion, and you could convert it into joules per nucleon as well if you wanted to, and get that way. So there's two ways you can kind of do it. Einstein's equation using Avogadro's number to the 26th, or you could just use those two kind of conversions there and first go into mega electron volts and then go into joules if you need to go into joules by using that conversion as well. Any questions on that there? All right. So let's take a look at one here. Actually, let's take a look at this. As I mentioned before, the nuclear binding energy per nucleon is also a measure of stability. And again, the higher the binding energy per nucleon, the more stable it is. As you can kind of see here on this guy, higher in 56 is kind of the champ there in terms of binding energy per nucleon. It is the most stable. And again, you can see that here. Things will kind of do fusion or fission to try to get themselves into a nice stable area. But again, it is definitely a measure of stability, having a higher binding energy per nucleon. So I tell you what, why don't we take a break for now? Okay, we're going to continue on. Any questions so far on what we've been talking about? Oh, come here. All right, so we're talking about nuclear binding energy. So why don't you give it a try there? We want to calculate the mass defect and the nuclear binding energy per nucleon in mega electron volts. Why don't we do both? Let's do mega electron volts per nucleon and joules per nucleon as well. And we'll give you some protons and neutrons masses there. All right, so why don't you give it a go, see what you come up with. Carbon's number 6 on the periodic table. Okay, so let's take a look. So again, we are looking at carbon here. 16 mass number. Once again, we could get our atomic number there from the periodic table, number 6. Um, that's going to help us get our protons and neutrons, which is what we need for our mass defect. So obviously our protons here are going to be 6, and our neutrons would be mass number minus atomic number, going to get us 10 in this case. So we can get our mass defect here by calculating the difference between our protons and neutrons and the mass of the isotope. So 6 times the mass of a proton here, 1.00783 AMU, plus 10 times the mass of a neutron, 1.00866 AMU. That then is going to be subtracted from the atomic mass there of our isotope, which is 16.014701 AMU in this case. So we'll end up with 6 times 1.00783 plus 10 times 1.00866, about 16.133 minus 16.014701. Going to get us a mass defect of about 0.118, I'll call it 9 AMU. At this point, once again, you do have really two options. Again, you can use Einstein's equation, or you can use those conversions. So since we're looking for each, it doesn't really matter, but we'll go with the conversions here first. 1189 AMU. Again, 1 AMU of mass defect equals 931.5 mega electron volts. So if we take that and times it by 931.5, about 110.7 mega electron volts. Remember, we want it per nucleon, so we're going to divide it by the nucleon, which is essentially the mass number, the protons and neutrons. So this would be 16 nucleon. And if we do that there, looks like about a 6.921 mega electron volt per nucleon. We also can then convert it into joules per nucleon by using the other conversion that we had there. So really, we're going to take 1 mega electron volt, 1.602 times 10 to the minus 13 joules. So we'll take 1.602 to the minus 13. That'll give us something like 1.11 times 10 to the minus 12 joules per nucleon here. Any questions on that? Again, if you took Einstein's approach, you would do something like E is equal to 0.1189 AMU times our 3 times 10 to the 8 meters per second squared. And that'll get you 0.1189. 1.070 times 10 to the 16 AMU meter squared second squared. then you would use your Avogadro's number to the 26 AMU per kilogram. And that should get us really to our joule number. Again, might be slightly different with some rounding there, but should get us there. And divided by our 16 will get us there. So that gets you 1.77, I'll call it 7 times 10 to the minus 11 joules divided by our 16 nucleon gets us there. Back that way, yeah. Any questions on that one there? And obviously at that point you could use conversion to go to mega electron volts, which should get you to the top one if you kind of went that direction. All right, let's take a look at another one here. Calculate the binding energy per nucleon of iron 56. Atomic mass there 55.93494 AMU. Again, a proton 1.007825 AMU. And a neutron 1.008665 AMU for a neutron there. And iron obviously is 26 there on the periodic table. All right, so let's take a look at this one here. So iron 56, we'll get our protons and our neutrons. So obviously here from the periodic table, that's going to give us 26 protons. For our neutrons, you're going to go mass number, which is this number right here, which is 56, minus our atomic number, which is 26. And that does look like 30 neutrons in this case. Again, that's going to allow us to calculate the mass defect, which is that difference of mass is going to get converted into energy here. So our mass defect in this case going to be 26 times our atomic mass for a proton 1.007825 AMU plus our 30 times our neutrons mass there 1.008665. Again, we're going to subtract that from the isotopes mass there, 55.93494 AMU. A lot of numbers. And if we do that there, 26 times 1.007825 plus 30 times 1.008665 minus a 55.93494. Going to get us a mass defect of 0.52846. Again, didn't really specify here, so we'll go mega electron volts first. And as I showed before, you can't do it either way, but we'll just go conversion here. So again, 1 AMU of atomic mass unit, a mass defect, will get us our 931.5 mega electron volts. And that's going to get us here about 492.3 mega electron volts, again, divided by our nucleons, which is basically your mass number in this case, 56 nucleons, which is our protons and neutrons. And that's going to get us an 8.790 mega electron volts per nucleon. Once again, if you did want joules, you can again use that conversion there and convert it out. 1 mega electron volt, 1.602 times 10 to the minus 13 joules. And that'll get us something like 1.41 times 10 to the minus 12 joules per nucleon. In this case, nucleon. And any questions on calculating that there? Now, as I mentioned before, and as we saw in those graphs, binding energy per nucleon also measures stability. So if we look at the three that we just calculated here, iron 56, I think it was fluorine 19, which was 7.789 mega electron volts per nucleon. and carbon 16, I think it was, 6.921 mega electron volts per nucleon. Again, we can see based on binding energy per nucleon, it is iron 56 that is the most stable based on our binding energy per nucleon. If you remember in those graphs that we saw where they kind of went up, that's why we saw iron 56 up there on top. It is the most stable in terms of these based on binding energy per nucleon. Now, these three, the carbon 16 would be the least stable of those three based on binding energy per nucleon. Any questions on that there? Next thing we're going to talk about is nuclear transmutation. And transmutation is basically an idea of kind of like shoot particles at other things and they get a little upset and perhaps make new things. One way you could do that is with a particle accelerator, has a magnetic field and an electrical field, and basically get the particles spinning really quickly, moving really quickly based on that, and then you could shoot it at its target. And that is how we get, a lot of those elements that we find there on the bottom of the periodic table with all the interesting names like berkelium, californium, einsteinium, all those things. As you can see, these are all transmutation. Basically, we're taking a particle, for example, like a neutron in that case, or even an alpha particle, or a bunch of neutrons, and we shoot it at these sort of parent nuclei, and they will go through a fission process and produce, as you can see there, our californium, there it is, our einsteinium, and so forth, these kind of new elements. So these are sort of the man-made elements, if you will, and how it's sort of accomplished through this process of basically shooting a particle at a other element or nucleus, and again, going to kind of transform it into this sort of man-made one. As you can also see, it also gives off other particles in certain cases, like beta particles and neutrons as well in this sort of process. And that is also how you can, as I mentioned earlier, sort of kick off, for example, a fission reaction. And again, a fission reaction is really where we have sort of a nucleus that will really undergo sort of decay into two new nucleuses. So, for example, if you take uranium 235 here and you shoot a neutron at it, it becomes like a bowling pin, a little unhappiness there, and it will then split off into two new nucleuses. It will also produce some neutrons in that process as well, and a lot of energy process given off in that situation as well. And just for comparison, you can see there per uranium 235, you get about 3.3 times 10 to the minus 11 joules per uranium, which basically accounts to about 2 times 10 to the 13 joules per mole of uranium. In comparison, if you looked at the combustion of coal, which is kind of blocked up there, 1 ton of coal, you get about 5 times 10 to the 7 joules of energy for the same ton of coal. And obviously, you can see you get a lot more energy out in a fission reaction. The comparison of why they compared, for example, coal to uranium. Traditional power plant uses coal basically to power the power plant or to make power. And obviously, in a nuclear power plant, they use a fission reaction to do so, and you obviously generate a lot more energy in a fission reaction. Now, as I might have mentioned previously as well, when you do a fission reaction, because it does break apart into these two new nucleuses, you actually don't always get the same two guys that kind of pop out. So it's not always consistent on what you actually do produce. But there are some common mass numbers that do sort of come out, relatively consistently. But you can get a sort of potpourri of different things that will pop out in a fission reaction. So you may not always get the same sort of two elements. You typically will usually get, though, neutrons and energy, obviously, that comes off for sure in this type of reaction. Now, In a fission reaction, we can have what is sometimes referred to as a nuclear chain reaction. And a nuclear chain reaction is basically a self-sustaining fission reaction where basically it just kind of keeps going and sort of exponentially growing. So if you think about sort of the fission reaction to kick it off, you kind of shoot like a neutron at like uranium, for example. And obviously that splits it off into our new nucleuses, and you produce a bunch of neutrons and energy, obviously, in that process. The deal with this is, since it is actually like a neutron that kicks off this reaction and you're producing a bunch of neutrons, that's not going to stop them from coming back around and basically continuing this process to continue, to continue, to continue. And if you have a critical mass of something like uranium, that's fissionable, it will continue to grow. So as you can see here, we kick off this reaction, it splits, more neutrons that can then hit other uraniums, and you continue to sort of exponentially sort of grow this reaction and continue to do so. Every time it sort of does the fission reaction, it obviously releases a good amount of energy. It also produces a lot of radioactive sort of byproducts and products that are made as a result of this, which can give off obviously a lot of energy. That's the idea behind sort of like a nuclear sort of bomb there. You have a non-critical amount of something like uranium in it. And with a non-critical mass of something like uranium, they will not go out of control in a sense. So it'll be a little bit more controlled. But they are separated in this type of situation, and they have sort of explosives. So what happens when the bomb hits is the two non-critical parts join up. And now you actually do have a critical mass of uranium there, and that will cause this chain reaction to continue out and obviously produce a lot of radioactivity and a lot of energy that's not so good. As I mentioned before, this is also the same type of reaction that's used in a nuclear power plant. And power plants pretty much work very similar. Traditional power plants, nuclear power plants, you basically got water and you heat up the water, and the water makes steam. And steam goes out to the turbines, out to the generators, and then you get light. Yeah. And because it is steam and water, they kind of condense it back and kind of recycle it and kind of do that process over and over again. Difference is in a traditional power plant versus, say, a nuclear power plant is how they heat the water. In a traditional power plant, they burn coal and they use the energy from that to heat the water. In a nuclear power plant, they use like a fission reaction. And here's a schematic of it like a nuclear reactor. Our closest nuclear reactors, I think, there is in San Onofre there, right off the 5 freeway there. Not used so much anymore, but the big domes that you see after you get down by San Onofre. And inside there, there's kind of two parts to it. There's sort of the fission chamber there where they do that, and they basically have these fuel rods, and these fuel rods are like little rods that have erasers sort of sized pellets of uranium in there, and that's what causes the fission reaction to occur. That fission reaction heats up the water in this container here, which then is kind of tubed into another big container of water. And that heat is used obviously to heat the main tank of water, which obviously creates just the steam that goes out, obviously, to sort of power everything. Now, as I said before, a lot of times they like to cool that back down, which is why traditionally nuclear power plants were usually built by big bodies of water, like in San Onofre, where you have the ocean next to it to use the water there to cool it back down. If you're more inland, like in Arizona off the 10 there, they have nuclear power plant over there by Palo Verde. They usually have very big cooling towers of water and stuff like that that they use to sort of do that. Um, and ideally here to keep kind of the radioactive part away from the sort of water part. Now, why does this reaction not really go out of control and do sort of a chain reaction when you have a nuclear power plant? Because typically they keep the mass as non-critical, so They try to keep the mass uranium less than what's needed to sort of keep the reaction going. And they also have in their other rods, which are known as control rods. And control rods are dipped in things like cadmium, and cadmium's actually a really good neutron absorber. And why would something that's a really good neutron absorber be really good in this reaction? It's because if you think about how this reaction starts, it's neutrons that kind of kick it off, right? And get it going and start splitting. And then you also produce more neutrons. So with these control rods, they could kind of take some of the neutrons out of the equation and again, try to keep the reaction under control. So it's not just, bellowing out of control and building out. Obviously, there's good and bad to both of those, right? Coal usually not so clean when you burn it. Also, it's to strip a lot of the land there to get to the coal. And nuclear power plants, obviously, it creates a lot of radioactive waste, right? And what you do with all that stuff and how long it sticks around. For a lot of years, nobody wanted that stuff to be moved near their neighborhoods or past their neighborhoods to go anywhere. So for many, many years, they used to keep all that stuff just like on site pretty much. Uh, a number of years down out there in Nevada, they built a big hole, and that's where they kind of put a lot of it now. It's how they get all the neon lights to stay on there in Vegas and all that good stuff. Um, a lot of our nuclear reactors and uh, for power plants are sort of decommissioned because there's a lot of upkeep and money that they don't want to pay to kind of get it up to code and stuff like that. So really, a lot of ours are not even really functioning these day and age. As I mentioned before, they're sort of good and bad for both. They both can produce a lot of waste. And in the case of a nuclear fission, they produce a lot of what is sometimes referred to as spent fuel. And these spent fuels are really the stuff that are sort of produced as a result of these fission reactions, those sort of products that are produced. The problem with a lot of that stuff is, as you can see on this little chart here, it takes a lot of years to store these things, and they're still fairly, very hazardous and radioactive for a very, very, very long time. So that was, a very big problem for that of who's in charge of it, who keeps it under control, where do you put it? And so again, sort of downside to both of those sort of types of things. Now, the next thing we're going to talk about is fusion, which is a little bit different than fission. In fission, we sort of split off a nucleus into two new ones. In fusion, much like the name implies, we actually take two smaller guys and kind of combo them together to make a larger sort of nucleus. This happens at very, very, very high temperatures, like, hey, I'm vacationing on the sun type temperatures, is what's just necessary for this. That is why in a lot of those movies, they always want the guy that could do cold fusion, right? And not what you normally need, which is I got to go to the sun and something like that hot to do it. But here again, kind of two smaller guys making a larger sort of element. We also obviously use radioisotopes in medicine. And when we do use it in medicine, obviously we're looking for things that have a very short half-life usually, because again, if it has a very long half-life, that's going to be a very long follow-up appointment. The nice thing about radioactive sort of isotopes of elements are really they do perform the same sort of chemistries in your body as the sort of non-radioactive isotopes. So you can use it to sort of follow what's happening or highlight certain areas. So for example, sodium-24 is a blood flow tracer that's used. And again, by following the radioactivity, you can sort of highlight the areas, say in the body and stuff like that. Iodine-131 for the thyroid gland. Fluorine-18 there for positron emission, and technetium for some imaging. And again, you can see it just sort of highlights some of the stuff there on the scans. Also used in just a regular sort of laboratories as well. People that do research, for example, on proteins and stuff like that, they oftentimes will use radioactive versions of elements so they could follow the radioactivity to see what's happening. I used to do research with radioactive copper 64, copper 68, and we would label proteins with it or do it with um, those guys so we could follow the radioactivity, see exactly where the copper went throughout all the protein purification process and stuff like that by just following the radioactivity. Again, some more examples here. Bone scan there, really highlighting all those areas. Typically, if you've ever used anything that's radioactive, you also will use what is sometimes referred to as a Geiger counter, and it's got a little wand and a little box usually, and makes like a little noise, starts to beep, beep, beep. You point it at yourself, it beeps a lot. Hopefully not. You don't really want that to happen. You point it at your shoes before you leave. It's usually a good idea. But usually when you clean up, you do want to go around with the Geiger counter a lot of times and just kind of wand everything, make sure things are okay. If it's making a really loud noise, it's probably pretty radioactive still. Um, Also, if you work with radioactivity, a lot of times they will give you a little ring to wear and a little badge. And every so often they develop it just to make sure you haven't been exposed to too much. It used to be like X-ray film sort of thing. And they go, well, you should maybe take a few days off of your research there since, you're probably glowing. And so, but a lot of people aren't really in bad shape, but they oftentimes will just leave their lab coat with that on right next to their experiment and not really be in it. And then they get it developed and go, oh, that's not so good. By the way, a safety thing, right? If you ever are working with radioactivity, make sure you understand what type of emitter it is, what type of safety that you need. Sometimes people don't tell you the right things there. And obviously, exposure is a very big thing. You don't want to be hanging around it for a very long period of time. Speaking of exposure, we sometimes look at two types of sort of exposure. A RAD is a radiation absorbed dose, and a REM is sort of the equivalent per man. So you kind of take your RAD times it by the quality factor. Remember that we saw, I think, a slide earlier on that depending if it's sort of a gamma ray, beta, or alpha, they do penetrate further in lead, and they also penetrate further in your body as well if you're exposed to it as well. Um, by the way, if I hold up the Geiger counter, it will make some noise, hopefully not too loud noise. There is background radiation, right? So it will click a little bit. That's also what you hear when people are doing the lab. Oh, it's just background radiation. Don't worry about that sound. You're all right. But here, as you can see from this table, we do get exposed to some radiation, ground and surroundings, X-rays, air travel. You happen to live near some nuclear waste or a weapons testing area, you get a little bit more as well. That's strawberries. Good talk. Any questions on that there? All right, that wraps up chapter 18.